Thank you, Mr. Chairman. Hello, everyone. Today I will talk a bit about laminography and digital volume correlation applied to sheet samples made of aluminum alloys. It has been commonly reported during the mode 1 opening of the compactation specimens that the final crack starts to propagate in a flat manner, then it tilts and continues in the slanted manner. Compared with the same specimens broken under pure mode 1 condition, this results in a reduced toughness. So this was the main motivation for us to try to understand the origin of this flat to slant transition in the context of ductile damage evolution. So first I will say a few words about laminography and digital volume correlation. Next I will outline some details of the experiment, and in the second part I will present some results both from the region far away from the notch and the region in the immediate vicinity of the notch root. So unlike tomography, which is limited to stick-like sample scanning, laminography enables us scanning of laterally extended objects. In the context of mechanical experiments, this means that we can use flat specimens. When we use flat specimens, we can apply more engineering relevant boundary conditions. So the object is rotated around its axis while the projections radiographs are acquired, and these radiographs are used they are used with the help of specially developed back projection algorithms to build the reconstructed volumes, as shown here. Constructed volume is nothing else than a spatial scalar function of the gray level values. And the basic principle of digital volume correlation consists in the matching of gray levels in the undeformed configuration F with the one in the formed configuration G, but corrected with the displacement field that we are looking for. So unlike most of the commercial codes that are using a local approach to image correlation, here we have used a global approach, meaning global in the sense that the residual that we are trying to minimize, and this is the difference between the two, is minimized over the whole region of interest in a single approach. To be able to do something like that, we need to decompose our displacement field that we are looking for on some kinematic basis. In this work, we have used the kinematic basis from finite element methods associated with the hexahedral elements and corresponding trilinear shape functions. As you can see, or you cannot see, we have poor contrast. So it's a challenging task for digital volume correlation. Still, there is enough contrast to obtain some good results, and this contrast is mainly due to these white intermetallic particles that are present in this aluminum alloys. On the other side, in this aluminum alloy, we have almost no porosity at the beginning of the loading process. So here you can see the sample. It is a CT-like specimen, and it has thickness of 1 millimeter, while the radius of the machined notch is 0.17 millimeters. The material is the aluminium copper lithium aluminum alloy, and heat treatment is T8, which endows high yield point and low work hardening. So here you can also see the loading device. So we are applying load by moving these two screws, and we are talking about stepwise loading procedure. So after each loading step, we are scanning, and we are scanning always the same region, just ahead of the notch root. After the reconstruction, we end up with the reconstructed volume that is shown here. So this is the notch root, and this is the rest of the material just ahead of the notch root. We are talking about 1.5 millimeters cubic of the material here. But still, it's too much for us. So if we cannot conduct a DVC analysis on the full reconstructed volume, this is computationally too demanding. That's why we are extracting region of material, and then we are performing DVC on this part of the material. And first of these regions, shown in the red, ROI1, has been DVC analyses have been conducted, and the results have been published in 2014 in Acta Materialia. And here it has been shown that already from the first loading step on, we have a strain localization in the form of these slanted strain bands, while the onset of the damage growth, it has been shown only at the very late stage of the loading, just before the final slanted crack had propagated. So here, in this case, in the slanted region, so this ROI is roughly 800 micrometers from the initial launch route, so it is positioned in the slanted region. It has been shown that early strain localization precedes damage development. Our question was, what's happening when we go closer to the launch route? Does damage or does strain localization occurs first when we are in the immediate vicinity of the notch root? For that reason, we constructed another ROI 2 with the yellow. So this one is closer to the notch root. It is elongated in the crack propagation direction L, and consequently it has to be decreased in the true thickness direction to be able to perform DVC calculations. As I said, we have used the kinematic basis of hexahedral elements with the trilinear shape functions and element size of 16 voxels, where the physical size of one voxel is 0.7 micrometers. This configuration yields a standard strain resolution of 0.3%, which means that all the strain levels below this one cannot be deemed as trustworthy. Okay, on the left here, you can see notch opening displacement as a function of this stepwise loading procedure. So after the first loading step, in the underformed configuration, we have scanned the material in underformed configuration, and we have additional 4 scans after each of these loading steps. Since we have really complex kinematics that develops in the front of the notch root in the immediate vicinity, successful DVC calculations have been obtained for the first 3 incremental loading steps. And these 3 loading steps are shown here. So the first, second, and third incremental loading step. Here, we are looking at the von Mises strain maps that are plotted on the section that is normal to crack propagation direction. So this is the direction of the opening, and this is the direction of the crack propagation. And D denotes the distance from the initial notch root. So we can see that already at the first incremental loading step, when the notch opening displacement is around 15 microns, and already 250 microns from the initial notch root, we have onset of this localized strain pattern. This strain pattern is rather complex, and in the sense that very close to the notch root in the immediate vicinity, we have this one huge horizontal band, and very soon it develops to these several strained slanted bands. When going farther away from the notch root, we are arriving to the slanted zone, and here in the slanted zone, mainly one X-shaped slanted band remains. Spacing between the bands is roughly 200 microns, and the bands itself are between 15 and 100 microns. While the grain structure reveals that the dimension of the grains in the thickness direction is between 10 to 30 microns, meaning that these reported slanted bands are spread over multiple grains. You can do the same thing, so plot von Mises strain maps for the 3 loading step, but on the section that is normal to thickness direction. So in the middle column, we are observing mid-thickness section of the specimen, and on the left and on the right, we are observing the sections that are close to the surface. So we can observe these 3 horizontal strained bands, and an interesting thing is to observe this temporal activity of the bands. So in the first loading step, middle one and the upper one are mostly active. Then in the second loading step, the activity is shifted down, while on the third loading step, activity is again in the middle and the upper horizontal band. Also, it's interesting to see how does it change when we go from the surface to the mid-thickness and again to the surface. So we have this distribution, then in the middle again, and then again. Actually, this confirms the slanted strain band position as has been shown in the previous slide, or as you can see here. If we plot strain profiles along the line that is positioned roughly 300 microns from the initial notch root, as is shown here, we are obtaining a strain profile shown here. Strain levels in the band, so the ratio between the strain level in the band and outside of the band is roughly 2, meaning that the part of the material outside of the band does not experience elastic relaxation. It also deforms, but with strain rate that is lower than for the material that is in the band. But what about the normal strains? So if we plot normal strains in the crack propagation, in the loading direction, in the thickness direction, or in the crack propagation direction, we have sections as is shown here. Here I also plotted von Mises strain maps just for the comparisons. and now we are observing section, mid-thickness section of the specimen. So this is the position of the initial notch root, this is the opening and the crack propagation direction. We can see that the normal strains in the loading direction and the normal strains in the true thickness direction are mainly responsible for the observed strain band pattern, or von Mises strain map. And it's also interesting to see how these contraction zones in the true thickness direction corresponds well with the position of the equivalent strain bands. On the other side, normal strains in the crack propagation direction are mostly zero, except this region close to the notch where necking occurs. The next step, we can plot strain profiles along this section with the normal strains in crack propagation direction. And this is done here. So we are plotting strain profiles along these three lines. And we can see that reaching the full plane strain condition, that is after this necking, so 250 microns from the initial notch root, it corresponds well with the onset of these slanted strain bands. So this confirms that the plane strain condition, but plane strain condition in crack propagation direction, actually it's friendly for the strain localization. Okay, here we have shown that the strain bands are there from the beginning of the loading process, but the open question is what's happening with the damage at the same time. So for this purpose, now we are observing void distribution in the initial state of the void that we are following. So we have first loading step, almost nothing happened in terms of the void growth, while we already have localization. Then second loading step, some damage growth. And then only after third loading step, there is damage growth, but mainly concentrated in the zone very close to the notch root, where we have high stress reaccelerates. So we conclude that here strain localization is not induced by damage mechanisms. It's interesting to plot von Mises strain maps over the final failure position. So we have done this for the three loading steps and for the sections that are normal to crack propagation direction, as is shown here. And it's we can often question how far can one go in predicting the failure mode by observing just incremental plastic activity, because here is shown that the localized strain pattern really resulted in a zigzag failure already from the beginning of its propagation that follows well the early prescribed strain band pattern. So I will show you just two movies here. So we will observe the von Mises strain maps in the section normal to crack propagation direction. We will start from the notch root and going further away in the slanted region. Can you just run the video? So already very soon after the notch root, we have this onset of the strain bands, and this pattern is going to be more simpler when we go to the slanted region where only one X-shaped slanted band remains. Also, we can observe the same thing for the true thickness direction. So we have this horizontal band, and we can observe this intense dynamic activity of the horizontal bands. So I will conclude. So in this work, a plastic zone ahead of the notch root has been assessed by using in situ laminography and digital volume correlation. We have shown, we have found interesting strain fields that reveal complex localized pattern in the slanted zone, but also in the zone close to the notch root. And we can say that onset and development of slanted strain bands precedes damage. That points out that plasticity is the driving mechanism for flat to slant transition, at least in this group of the materials. So it's an interesting piece of information, but the physical background is still not clear. One of the possible explanations will be shown in the following presentation. Thank you for your attention.